Hey there, today we are talking about section 5.1, which is applications of derivatives, chapter 5. We are doing extreme value of functions. When you are finished with this section, you'll be able to find local extreme values and find absolute extreme values. So, oops, I clicked too many. Absolute extreme values. So f be a function with domain D, then f of c, so that's a value, a y value, is the absolute maximum if and only if f of c is the largest number in that domain. And then, of course, it's an absolute minimum when it's the smallest value in the domain. That's what that notation means. So if you need this, pause it, write it down. The extreme value theorem, EVT. So this is a big one. You do want to pause this and write it down to make sure that you have it. So if f is continuous on a closed interval, so continuous and closed, f has both a maximum and a minimum value. So continuous and closed, it's going to have a maximum and a minimum value. So from A to B here, it has both a maximum and a minimum value, looking at all of the critical points on it and the endpoints. So here we have a closed interval from A to B. We have a maximum and a minimum right at the endpoints. Nothing happens in between there. On these examples down here, we have, if this is closed from A to B, we have a minimum and maximum. This guy is just a local. It's not an absolute. This one is a local. That one's our absolute minimum. And then, of course, our absolute maximum. So classifying extreme values. So if this is our function here, we have values on it. Again, you've seen these. We started talking about these in Algebra 2. So we have absolute minimums, absolute maximums, and then local min and max. So absolute is there are no other values higher than it or lower than it if it's a max or min. And then your local is in that area, that's going to be a maximum. So like in this area, it's a maximum. In this area, it's a minimum. Okay, but not overall. So our local extreme value, C is an interior point of the domain on the function, then f of c is a local maximum at c if and only if f of c is a maximum value on the open interval. So on the open interval. And then, of course, the local minimum works the same way. So a function f has a local maximum or a local minimum at an endpoint if the appropriate inequality holds for all x values. So it's going to be a local max or a local min if the values are, so like this guy is a local minimum because all the values before it were greater than it. So it's smaller than the values above it. Okay. So that's just what they're talking about when they're talking about endpoints. Local extreme values. So if a function f has a local maximum value or a local minimum value at an interior point C of its domain, and if the derivative of f exists at C, then f prime of C equals 0. So this is a huge thing. So f prime of C equals 0 if it's a max or a minimum in the interior and your derivative exists. So critical points, also a big one, because we're going to use critical points to test values and to find our maximums and our minimums and eventually our point of inflections. So a point in the interior of the domain of a function at which f prime is either equal to 0 or doesn't exist. It's a critical point. So what that means is it has to be continuous, of course, but when it wouldn't exist, we'd have a vertical tangent, we'd have a cusp, we've had a corner, that's where it wouldn't exist. Otherwise, it's going to be 0, so it comes up to a maximum and it rolls back down, so the slope at that very top point is going to be 0, or it can come up to a peak, like a cusp, and it won't, the slope won't exist up there, the derivative won't exist, However, it's still a critical point. Finding the absolute maximum and absolute minimum values on the interval. So it is closed. This guy is continuous. We need to find the critical points of your derivative. So here's the derivative. They found it for us, and it doesn't have any zeros. No zeros, but it's undefined at x equals 0. So we are checking our critical points and our end points, sorry. So we have one critical point at x equals 0, and we have our endpoints at -1 and -2. So we check our critical point, put that value of x back into the original, we got 0. Put the endpoints into the original, we get 3 and then 4.762, and we are determining the absolute max and min. Well, these are the only values that we're choosing from because these are the only potential values we could have for maximums and minimums. So we want to just look at them. Which one's the max? Well, this guy. And which one's the min? Well, the critical point. So the absolute maximum value is the y value here. It occurs at x equals 2, and then the absolute minimum is 0. It happens at x equals 0. So we just need to first go through, find your critical points, and then test your critical points and your endpoints in the original function to determine which one's the absolute max or absolute minimum. All right, finally, we're finding extreme values. So maximums and minimums again. What's absolute, what's local, what do we have? So here is our function. F is defined for all values where 9 minus x squared is greater than 0 because it's the square root. So the domain on the interval is between -3 and 3. So in that interval. Since the domain has no endpoints, it's not closed, we are not guaranteed to have absolute max or min at the endpoints or even local. So extreme values must occur at the critical points. It's not defined at the end, so they're open circles at the end. We can't include those as critical points or endpoints that we're looking for. Okay, so we are going to find our derivative. Here it is. And then the only critical point is at x equals 0. That's the only potential point that could happen. So put x equals 0 in, we get 1/3. To determine whether it is an extreme value, you need to test some values around it. So what's happening? Is it a local minimum or an absolute minimum? Then the values around it are going to be greater than it, or vice versa. Maybe it's a maximum, then the values around it are going to be less than that. So you just need to make sure that you are going through and seeing what happens. So it says as x moves away from 0 on either side. So as we go more positive or more negative, the denominator gets smaller and the values of f increase and the graph rises. Therefore, there is an absolute minimum at x equals 0. Okay? Good. That's it for today's lesson, and we will do lots of examples in class.